So, picture this. In July 2026, there was this rogue AI agent, right? And it got stuck in this massive infinite research loop.
Oh, yeah, the $1 million loop.
Exactly. It burned through $1 million in cloud computing fees in like under an hour. And the crazy thing is, it didn't happen because the AI was malicious.
Right, it wasn't a hack or anything.
No, not at all. It happened because the actual architecture of intelligence itself, like the way we wire these systems together, is just completely broken. So, welcome to the deep dive. Today we're opening up the engine room of modern AI.
It's long overdue, honestly.
Yeah, I mean, whether you're prepping for some high-stakes technical architecture meeting, or you just want to know where the industry is heading, or even if you're just insanely curious about the bleeding edge of artificial intelligence, this is for you. We are tackling a massive evolution in the tech world today.
We really are, and our stack of sources for this deep dive all center around one highly overloaded concept, which is graphs.
Graphs, which honestly might be the most misunderstood word in tech right now.
It easily is the most critical and misunderstood term in software today. I mean, we're witnessing a fundamental shift here. Software isn't just processing rows and columns of data anymore. It is simulating organizations. It's simulating structured reasoning.
Right. And to make that leap, AI needs structure, it needs memory, and as that $1 million mistake proved, it desperately needs governance.
Desperately.
So we're going to trace this entire ecosystem from the bottom up today. We'll explore, how we store complex data, how we teach AI to actually understand that data through knowledge engineering, and how we're moving from these single frantic AI agents to entire AI org charts.
Which is a movement called graph engineering.
Exactly. And finally, we'll get into how we govern all of this chaos using reference architectures. But okay, let's unpack this. Before we can build an army of AI agents, we really need to understand where their brain power lives.
You have to start in the basement.
Yeah.
The engine room.
Right. And in the data world, that engine room is the database. Our sources go really deep into the architectural differences between the heavy hitters here. We're talking AWS Neptune, Neo4j, and this major disruptor called FalCoreDB.
Yeah, so let's set the stage with why we even need graph databases in the first place. When you're dealing with AI, you're fundamentally dealing with relationships. How does concept A relate to concept B?
Okay.
Relational databases, like your classic SQL tables with rows and columns, they struggle immensely when relationships get too complex.
Like if you're trying to figure out who bought a product, right?
Right, if you just want to know who bought a product, you run a simple join operation between a user table and a product table.
Yeah.
Easy. But if you want to find out who bought a product that was recommended by a friend of a friend,
Oh, man.
yeah, suddenly you are running multiple joins across massive tables. It gets incredibly slow. Graph databases fix this by treating the relationship itself as a first-class citizen.
Okay, that makes sense. And our FalCoreDB source breaks down the incumbents perfectly. Let's look at AWS Neptune first. So the defining feature of Neptune is that it was built natively for the cloud, and it relies on this thing called decoupled compute and storage.
Which is a massive deal for enterprise architecture.
Right, so it has a single primary writer instance and then up to 15 read replicas, and they all point to this unified shared storage volume that just automatically scales up to 128 gigabytes.
And it's a multi-model core, too. So it supports property graphs using Gremlin or RDF triples using SparkULO, which is vital for legacy systems.
But the decoupled storage is the real magic trick, right?
It is the architectural marvel there, yeah. In an old-school database, the processing power, the compute, and the hard drives, the storage, lived in the exact same physical box.
So if you ran out of storage, you were just out of luck.
You had to buy a bigger box. Even if you didn't need any more compute power, you had to upgrade the whole thing.
Okay, let me test an analogy on you to make sure I'm really grasping the mechanics here. Neptune decoupling compute from storage, it's kind of like having a giant, infinitely expanding library, which is the storage, right? And that's completely separate from the librarians, which are the compute.
I like where this is going.
So if 1 million people suddenly ask for books all at once, you don't need to build a bigger physical library to handle the crowd. You just instantly clone 15 more librarians to run into the stacks, fetch the data, and hand it back to the users.
That is actually a highly accurate way to visualize it. The library just expands its walls automatically when new books arrive, and you only pay for the extra librarians when you genuinely need them. For enterprise workloads, it is incredibly safe and highly scalable.
Okay, so that's Neptune. But then you have Neo4j. And Neo4j is like the pioneer of the native graph database. And they take a totally different approach. They don't use that librarian model at all.
No, not at all. Neo4j is built entirely around this concept called index-free adjacency.
Right, which sounds super dense. But my understanding is that in a standard database, if you want to find a related record, you have to consult this massive global index.
Usually a B-tree index, yeah.
It's like looking up a topic in the index at the back of a massive textbook, finding the page number, and then flipping to that exact page.
Exactly. And if you have a billion records, that master index is huge. Searching it takes time. But Neo4j skips that master index entirely.
Wow, entirely.
Yeah. When you create a relationship in Neo4j, the nodes store physical memory pointers directly to their neighboring records.
Okay, so if Neptune is the expanding library, Neo4j is like a perfectly organized filing cabinet where every single file is physically stapled to its related files.
Stapled together, yeah.
So you never check a master index. You just pull one file, and a literal string leads you directly to the next one.
The technical term is pointer chasing.
Yeah.
And the huge benefit here is that the latency only scales with the size of the specific web you're exploring, not the size of the entire database.
Oh, I see.
Yeah, so if you are just following the staples between 3 files, the speed is exactly the same whether there are 10 files or 10 million files in the total cabinet. Plus, Neo4j uses causal clustering.
Which means what, exactly?
It gives you absolute guarantees that if you write a piece of data, you can immediately read it back across the distributed cluster. No replication lag.
Okay, hold on. I need to push back here for a second.
Sure, go ahead.
If both of these architectures are so phenomenal, like the infinitely expanding library and the perfectly stapled filing cabinet, why is our source material pointing out these severe critical bottlenecks for modern AI? Are these legacy systems already outdated for what we're doing in 2026?
Well, they aren't outdated for traditional software,
That
but for
makes-
AI.
Yes.
What's fascinating here is that the exact architectural choices that made them great are now becoming massive liabilities.
How so?
Let's look at Neptune's decoupled storage. When your librarians are completely separate from the library, what happens? They literally have to walk across the building to get the book.
Right.
In computing, that's a network boundary. Every single time an AI agent wants to traverse a complex graph to find a relationship, it has to cross a network. And that introduces network coordination latency.
Oh, so it adds up.
Big time. When an AI is trying to traverse thousands of connections in a fraction of a second to answer a prompt, those physical network trips stack up into a massive bottleneck.
Okay, but Neo4j doesn't have that network boundary issue, right? Because the pointers are local. The files are stapled together in the same cabinet.
True. But Neo4j has a different problem. It's deeply tied to a Java virtual machine architecture, the JVM.
And JVMs are heavy.
Very heavy. A JVM requires something called a memory heap, which is this massive chunk of pre-allocated RAM just to run efficiently. Furthermore, Java relies on garbage collection to manage that memory.
Which causes it to stutter, right?
Exactly. Causes these unpredictable latency spikes when the system essentially pauses to clean up. But the real killer for generative AI is the cold start.
Ah, the cold start.
Yeah, when a serverless function spins up to answer an AI prompt, Neo4j can take upwards of 90 milliseconds just to warm up and accept its very first query.
90 milliseconds. I mean, to a human being, that is literally a blink of an eye. You wouldn't even notice it.
To us, yes, it's nothing. But
Yeah.
you have to view this through the lens of a modern graph retrieval augmented generation pipeline, GraphRag.
Right.
In these pipelines, an AI agent doesn't just make one query. It might spin up, query the database dozens of times, synthesize the context, run another conditional query, and then pass it all to the large language model.
So if every cold start and every subquery hits a 90 millisecond wall,
The stack.
yeah.
Suddenly, your user is staring at a loading spinner for 5 seconds. And in the AI world, a 5-second delay means your product is dead.
Which brings us to the disruptor in the sources. FalkRDB. Our sources frame it as this high-performance alternative that fundamentally changes the physics of how the database works.
It really does. It completely abandons pointer chasing.
So no stapled files.
No stapled files. Instead, it uses sparse adjacency matrices and something called GraphBLAS, which stands for Basic Linear Algebra Subprograms.
Okay, I want to dig into the mechanics of that because it sounds wild. How does turning a web of data points into a giant grid of numbers actually speed up the computer? Like, what is the CPU doing differently here?
Think about pointer chasing for a second. The CPU reads a file, finds the pointer, goes to the next memory address, reads that file, finds the next pointer.
It's one after the other.
Exactly. It is strictly sequential. It is fundamentally serialized work. But linear algebra, specifically matrix multiplication, is something modern processors, especially vector processing units, are explicitly designed to do in parallel.
So it does it all at once.
Yes. When you multiply a matrix representing your graph by a vector representing your search query, you're evaluating thousands of potential paths simultaneously in a single CPU clock cycle.
That is insane. And a sparse matrix just means that most of the graph has no connections, right?
Yeah.
So the matrix is mostly zeros, which they compress to save memory.
Precisely. By compressing out the zeros, they can fit massive graphs into incredibly small memory footprints.
The stats in the source are just staggering. Falcor DB delivers up to a 496 times faster P50 latency compared to traditional engines.
496 times faster. Just let that sink in.
And because it uses those compressed sparse matrices, it uses up to 6 times less RAM than Neo4j's JVM heaps. But the craziest part to me is the cold start.
Oh, yeah.
It drops from 90 milliseconds down to 1.1 milliseconds.
Going from 90 to 1.1 milliseconds is literally the difference between a clunky, sluggish chatbot and an autonomous agent that feels like it's thinking in real time.
Hang on, I think I see the deeper connection here. If LLMs like, GPT or Claude are essentially just giant math engines under the hood,
They are.
they process words by converting them into tokens and then multiplying massive matrices of weights and parameters, and Falcor DB turns the database into a matrix multiplier. Are they essentially skipping a translation layer? Like, is the database just natively speaking the AI's mathematical language?
You've hit the nail on the head. That is exactly why this architectural shift is so profound. By moving graph traversals into linear algebra, Falcor DB speaks the native language of the AI era.
Wow.
It allows developers to integrate vector search directly within these graph schemas. An AI agent can retrieve structural, factual grounding in under 5 milliseconds. The database is no longer the bottleneck in the LLM pipeline. It becomes an extension of the LLM's own computational logic.
Okay, so we've established the engine room. If you want raw, blazing fast, serverless AI infrastructure, you move away from pointer chasing and you embrace sparse adjacency matrices.
Yeah.
But here's the problem. Raw data storage, no matter how fast it is completely useless if the AI doesn't understand what the data actually means.
That's the big catch.
I mean, I could have the fastest matrix multiplier on the planet, but if the AI retrieves the word bank and it doesn't know the difference between a financial bank you put money in and a river bank you fish from, the blazing speed just means it makes mistakes faster.
Exactly. Storing the data points and their connections is only step one. Structuring human knowledge so a machine can actually comprehend the semantics, the meaning of those relationships, is step two.
And that brings us to our next source from the Castle Lab. They explore knowledge graph and ontology engineering, or KGOE. What exactly are we engineering here?
Well, KGOE is the discipline of creating the conceptual maps that live inside these databases. We are just dumping raw text in there. We are building an ontology.
And an ontology is different from a simple taxonomy, right?
Very different. A taxonomy just categorizes things hierarchically. Like saying a dog is the type of mammal. That's a taxonomy. But an ontology defines the complex, multi-directional relationships and properties of an entire domain.
So it's much richer.
Much richer. It involves extending the map, populating it with data, aligning different maps together, and performing entity disambiguation.
Entity disambiguation meaning making sure the AI knows that John F. Kennedy, the person, is distinctly different from JFK, the airport in New York.
Exactly. And the foundational building block for all of this is the RDF triple.
Resource Description Framework.
Yes, a triple is incredibly simple at its core. It consists of a subject, a predicate, and an object.
So like Bob is the subject, knows is the predicate, and Alice is the object. Bob knows Alice.
Yes, that is the fundamental atom of semantic data. But when you start building real-world ontologies out of these triples, things get unimaginably massive.
And messy.
So messy. The Castle Lab paper points out that this has historically been a painfully labor-intensive process. Even after 25 years of semantic web research, these tasks defy total automation. You still need human domain experts sitting down and manually writing rules to resolve conflicts.
And the sheer size is the roadblock here. The source mentions the ENVO ontology, which maps environments and habitats. It has over 2,100 specific classes.
That's for environments.
Right, and then you look at DBpedia Core, which is essentially the structured, machine-readable version of Wikipedia. It contains roughly 900 million triples.
Just think about the cognitive load of that. Even a relatively small ontology with, say, 300 classes is completely beyond the working memory of a human engineer. You physically cannot hold the whole map in your head at once.
But wait, the promise of 2026 AI is that we have these massive large language models with context windows that can ingest entire books in seconds.
Right, the million token context windows.
Yeah. So why do we need humans involved in KGOE at all anymore? Why can't we just dump the entire 900 million triple DBpedia into the LLM's context window, give it a prompt and say, figure it out, map the connections?
Because LLMs suffer from cognitive overload just like humans do.
Really? Even with those huge context windows?
Yes. The attention mechanism inside a neural network, which is how it decides which words in a prompt are most important, gets spread far too thin when you feed it a monolithic, massive data set.
So it just loses focus.
Exactly. If you give an LLM an ontology with thousands of classes and ask it to align it with another massive ontology, the search space is simply too broad. The statistical weights get confused by all the competing noise, it loses the thread, and as a result, it starts hallucinating. It starts fabricating connections that just don't exist.
Which is where the researchers introduced the solution called MOMO, which stands for Modular Ontology Modeling. The philosophy here is basically divide and conquer.
Yes, exactly.
So instead of giving the AI the whole map of the world, you carve it up and give it conceptual, human-centric modules.
If you want an AI to understand the infrastructure of New York City, you don't give it a single map containing every single water pipe, subway tunnel, skyscraper, and hot dog stand all layered on top of each other.
It's unreadable.
It's completely unreadable. So instead, you give it a module called subway lines. You give it another module called electrical grid. You limit the scope to a single conceptually consistent domain.
Our sources share this brilliant illustrative story about this using a benchmark called the GeoLink Complex Ontology Alignment.
Oh, this is a great example.
Yeah, so researchers were trying to get an LLM to map complex rules between two distinct, highly technical ontologies used for oceanographic cruises.
Very niche stuff.
Super niche. First, they tried the brute force method. They gave the LLM the rule head, fed it both full ontologies, and basically just said, produce the alignment rule body.
And the result was disastrous.
Disastrous. The paper literally calls the output essentially unusable. Total slop. The LLM just couldn't handle the complexity. But then they changed the strategy to use MOMO.
They modularized it.
Right. They broke the ontology down into modules and prompted the LLM in two distinct stages. First, they gave the model 20 named modules, things like organization or physical sample or cruise, and simply asked the LLM to identify which modules were relevant to the task.
A much simpler task.
Exactly. And once the LLM picked the relevant modules, they prompted it again for the rule botter, but this time they only fed it the data from those specific modules.
And by doing that, they drastically reduced the noise. Do you remember what the success rate was?
It jumped to 95%. The LLM correctly identified 104 out of 109 target alignment mappings. It went from complete failure to near-perfect accuracy just by chunking the data.
That is a staggering improvement. And honestly, it tells us something profound about how these models actually think.
I really want to pull on that thread. Why exactly does chunking the data fix the hallucination problem? I mean, if the model has a massive context window, it physically has the capacity to read the whole thing. Why does it need us to hold its hand and cut its food into tiny pieces?
It's because we have a really bad habit of anthropomorphizing LLMs. We treat them like human researchers who could just sift through a messy desk to find what they need.
Right, we think they're reasoning like us.
But fundamentally, an LLM is a statistical engine predicting the next most likely token. That's it. When an LLM looks at the entire massive oceanographic ontology all at once, the probability space is huge.
So it gets confused by words that have multiple meanings.
Exactly. The word sample could statistically relate to a physical rock, a data sample, a water sample, or random statistical sample. Man, it gets muddy.
But when you give it the physical sample module,
When you isolate it to that module, the statistical sentiment of the prompt is tightly clustered around physical weights, measurements, and collection dates. The module acts as psychological guardrails for the LLM.
psychological guardrails, I love that.
It forces the math engine to stay within a very specific lane of probabilities. By narrowing the scope, you drastically reduce the chance of the LLM picking a statistically likely but factually incorrect token. Modularity creates conceptual consistency.
Okay, so modularity is the absolute secret to keeping an LLM focused when we are organizing its knowledge base. It stops the hallucinations when the AI is trying to comprehend data.
Right.
But comprehending data is passive. What happens when we ask LLMs to actually take action in the real world? It turns out you can't just let an agent run wild with a module. We have to apply that exact same modular philosophy to how they execute tasks, which brings us to the biggest architectural shift of mid-2026.
The shift from single autonomous agents to multi-agent organizations.
Yes. Our source from the AI Builder Club gives a phenomenal masterclass on this transition. They outline the industry's move from loop engineering to graph engineering. And to understand this paradigm shift, we need to walk through what they call the 5 layers of AI engineering.
This breakdown was fascinating because it really maps the chronological history of our frustrations with AI over the last few years.
It's a perfect evolutionary roadmap. Let's walk through it. Layer 1 is the prompt. This was the obsession of 2023. You engineer the exact wording of the request you send to the model.
You're constantly asking, am I asking this question well enough?
Right. Act as a professional marketer and write a tweet. But then we realized prompts aren't enough if the model doesn't know anything about our specific business. So we moved to layer 2, context.
This was 2024. This is RG Retrieval Augmented Generation.
Yeah, we started shoving PDFs and database queries into the prompt. You engineer what the model gets to see. Does it have the right information?
But reading isn't doing. So in 2025, we hit layer 3, the harness. We started giving the AI tools. We gave it access to web browsers, calculators, APIs, short-term memory.
The question became, can the AI act on the world and remember what it just did?
Which naturally led to layer 4, the loop. This dominated early 2026. Loop engineering is where you take a single agent, give it a goal, and put it in a while loop.
It creates a plan, takes an action, checks its own work against a verifier, and if it fails, it loops back and tries again until the task is done.
And that brings us to layer 5, the mid-2026 realization, graph. We realize that a single loop is fundamentally limited. Graph engineering is about the coordination between many specialized agents and deterministic steps.
The central question shifts from how does this agent do the task to who does what, in what order, and sharing what state.
Exactly.
Let's define the mechanics of graph engineering properly, because the term absolutely blew up on social media and caused a lot of confusion. A graph, in this context, consists of 3 distinct parts. First, you have nodes.
These are the units actually doing the work.
Right. A node could be a specialized LLM acting as a researcher or writer, or, importantly, it doesn't have to be an AI at all, right? It could just be a deterministic Python function that fetches an API.
Yes, the blending of agentic and deterministic code is crucial here.
Second, you have edges. This is the routing or the conditional logic between the nodes. If the reviewer node approves the draft, follow this edge to the publisher node. If it fails, follow this edge back to the writer node.
Simple enough.
And third, you have the shared state. This is the object traveling along the edges, like a shared JSON document or a dossier that every node reads from and writes to as it moves through the graph.
The defining characteristic of a graph is the isolation of responsibilities. You are no longer relying on a single LLM to hold the entire context, remember the instructions, and execute every single step of a complex process flawlessly.
The analogy used in the text, crediting a user named Rohit4verse, captures this perfectly. I look at it this way. Loop engineering is like hiring a frantic freelancer.
Oh, the frantic freelancer.
Yeah, you take one person and you tell them to research a massive 50-page market report, write the entire draft, fact-check their own work, format it, and edit it.
All at once.
Right. And eventually their working memory gets maxed out. They get exhausted, they lose the plot, and they start hallucinating facts just to finish the job.
Because the single agent gets overwhelmed by the context window and the shifting nature of the task. Asking an LLM to be highly creative while simultaneously asking it to be a rigid, skeptical fact-checker creates conflicting internal system prompts.
Right. But a graph is an org chart. You fire the frantic freelancer and you build a company. You hire a dedicated researcher node whose only system prompt is to blindly fan out and read 5 sources. They do nothing else.
That's research.
Then they pass their notes, the shared state, to a writer node. The writer drafts it. Then they pass the draft to a reviewer node. And this reviewer node can be a completely different model, maybe a smaller, cheaper model trained specifically for logic verification. And its only job is to be brutally skeptical and tear the draft apart.
It provides a much more robust, fault-tolerant way to engineer software. But we have to do a hype check here. As the AI Builder Club source points out, when the term graph engineering flooded Twitter and LinkedIn in July 2026, the backlash from veteran engineers was immediate and harsh.
Oh, it was brutal. Experts like Peter Steinberger and David K. Piano were calling out the massive influx of slop thought leadership articles.
They were not holding back.
The critics were essentially saying, congratulations, you just reinvented LangGraph or Google ADK or literally decades-old directed acyclic graphs and state machines. People were rolling their eyes, asking why the AI community was acting like routing state through conditional nodes was some brand new invention.
And well, to be fair, the critics were absolutely right about the underlying mechanics. The technology, state machines, orchestration engines, agent-to-agent communication protocols, none of that was invented in July 2026. LangGraph had been facilitating this for a year. The mechanics are old.
But the source argues that even if the mechanics are old, the design shift in how we approach AI is very real.
Exactly. Builders were genuinely hitting a wall. They spent the first half of 2026 trying to cram entirely too much complex logic into a single agent's loop, and those agents were failing catastrophically in production.
Hallucinating all over the place.
Yes. The shift to graph engineering isn't about downloading a new API. It is a cognitive shift for the developer. It's the realization that you have to design the topology of the system, the literal org chart, before you write a single prompt.
So practically speaking, how does a developer know when to just use a simple loop versus when to sit down and engineer a massive multi-agent graph? Because the source gives a very clear decision matrix to prevent over-engineering.
It does, and it's a crucial warning. If you have a single, well-scoped task with a clear finish line, for example, summarize this 10-page PDF, use a loop.
Keep it simple.
Keep it simple. One agent can easily read the file, summarize it, check its own work, and output the result. If you build a 5-node graph with a fetcher, a chunker, a summarizer, and a reviewer just to answer a basic customer support email, you are creating toxic overhead. You are spending 10 times more on API calls and adding unnecessary seconds of latency.
You don't need a massive corporate org chart to write a thank you note.
Precisely. But you must reach for a graph when the task splits into distinct specialties, or when you need parallelism.
Like fan out and fan in.
Yes. If your task requires an agent to research 5 distinct financial reports simultaneously, which is a fan-out operation, and then synthesize all of them together, a fan-in operation, a single loop will get horribly confused.
It'll just drop information.
Exactly. And if you need a separate model to act as a strict security reviewer to ensure personal data isn't leaked, you need an edge routing the state to a different node. You need a graph.
Okay, I want to transition here because drawing a cool AI org chart on a whiteboard is fun. Wiring up LangGraph on your laptop to write a blog post is an interesting weekend project. But bringing this into a Fortune 500 company,
That's a whole different ballgame.
running a fully autonomous multi-agent org chart in production is honestly terrifying.
It introduces a massive, unprecedented surface area for risk.
Think about the nightmare scenarios. How do you stop a rogue agent loop from encountering an error, failing to understand the error, and getting stuck in an infinite retry cycle where it fans out 100 times and spends $1 million in AWS API fees before you even wake up?
Or worse, how do you stop a researcher node from grabbing private, compliant customer data and handing it to a writer node that accidentally emails it to an external vendor?
Exactly. Moving from theoretical AI to enterprise reality is a harsh wake-up call for most developers. Production multi-agent graphs are this complex, messy mix of agentic callers making unpredictable decisions and deterministic functions executing code.
And because of that unpredictability, you need intense governance, cost control, and observability.
Which brings us to our true Foundry source on governing the agentic graph. It highlights exactly what infrastructure is required to keep these systems from imploding.
The first major enterprise requirement True Foundry highlights is identity. They argue that every single node in your graph needs a virtual account.
This is fundamental for security and auditability, right? Because in a traditional software system, if a user logs in and deletes a file, the system logs that user-specific ID.
Right.
In a multi-agent system, if a database gets dropped or an external API gets hammered, and the security team asks who did this, the answer cannot be the AI graph did it.
The graph isn't an employee you can fire or audit.
No.
You have to know which specific node executed the tool. The researcher node needs a fundamentally different identity and completely different permissions than the reviewer node.
Makes total sense.
So True Foundry utilizes virtual accounts so that every action, every LLM call, every database query, every tool invocation is tied to a specific node identity within the run of the graph.
Which leads directly into the second requirement, cost control. We mentioned the million-dollar fan-out mistake earlier. In a graph, edges can branch exponentially. One node kicks off 3 sub-agents, which each kick off 3 more.
And if an agent hits a rate limit error and just blindly decides to retry indefinitely, it can blow up your budget instantly.
So how does True Foundry solve that?
By mapping budget rules directly to those virtual accounts and metadata, you can hard cap the financial spend of a specific node or a specific run. If the graph hits $5 in API fees, it physically cannot invoke another tool.
It just cuts them off.
Exactly.
But the most fascinating security feature True Foundry discusses is the concept of structural checkpoints.
Oh, this is where we bridge the gap between AI autonomy and human accountability.
Explain how they define a structural checkpoint, because it seems kind of counterintuitive to the whole dream of autonomous AI.
Well, the autonomous dream assumes the AI is infallible. But in the enterprise reality, consequence concentrates at the edges of the graph.
What do you mean by that?
It's one thing if an agent hallucinates and drafts a bad internal summary of a meeting. That's a low consequence error. Nobody's getting fired over that. It's entirely another thing if the agent decides to execute a database migration or approve a refund or transfer funds to a vendor.
Yeah, those are massive consequences.
True Foundry implements structural checkpoints, which are essentially human-in-the-loop approval gates placed strategically right before sensitive actions.
So instead of relying entirely on the AI's internal reviewer node to verify the action, you replace that final step with an actual human hitting approve or reject.
Exactly. You let the multi-agent graph do 99% of the heavy lifting, the tedious research, the synthesis, the planning, the data formatting, but the actual execution of a high-consequence tool is gated.
But here's where we need to ask a critical question about system performance. Look at what we're doing here.
Okay, lay it on me.
We spent the first part of this deep dive talking about Felcore DB and how we need 1.1 millisecond storage engines to keep the AI blazing fast.
Right.
Now, to govern it, we are giving the agents virtual accounts, rigid budgets, rate limits, and literal middle management approval gates. Aren't we just recreating toxic, slow corporate bureaucracy inside our AI architectures? Are we artificially slowing down our 1.1 millisecond engines by slapping procurement approvals onto every agent?
I see where you're going, but I don't think it's bureaucracy. I think it is operational survival. If you don't do this, you lose the company.
Okay, fair. But what about the speed?
To address the speed issue, the True Foundry paper makes a very sharp, highly technical distinction regarding the separation of concerns. They separate the orchestrator from the gateway.
Break that down. How does separating them preserve the speed?
Well, the orchestrator, which is the framework actually running the graph, like LangGraph, owns the topology. It manages the shared state and tells the nodes when to fire. But the gateway, specifically something like True Foundry's MCP gateway, which handles the model context protocol, governs the tools, meaning the gateway just sits there checking badges. It doesn't run the AI, it just intercepts the API call, checks the virtual account budget, and either allows it or blocks it.
So by offloading the governance to a dedicated, highly optimized gateway, you minimize the latency impact on the AI's reasoning loop.
Yes. If you don't have stable graph, run, and node identifiers propagating from the orchestrator to that gateway, you have a massive liability. You have to be able to correlate the orchestration traces, what the graph thought it was doing in its logs, what the gateway's cost and policy records, what the graph actually did on the network.
That makes total sense. So by separating the execution layer from the governance layer, you maintain speed where possible, but you guarantee total auditability. You aren't slowing the database down. You are just ensuring the agent requesting the data is actually authorized to do so.
Exactly. Okay, let's zoom out and look at the monster we've just built.
It's a big one.
We've talked about mathematical matrix-based storage engines with Felcore DB. We've talked about engineering modular ontologies to keep the LLM sane using KGOE. We've talked about designing intricate multi-agent org charts with graph engineering, and we've just governed them with True Foundry gateways and human-in-the-loop checkpoints.
It is an incredibly deep stack. I mean, we've covered so many layers.
It is. And if building these systems requires this much intricate thought across so many completely different disciplines, we can't just wing it.
No, absolutely not.
A developer can't just sit down on a Monday morning and ad hoc their way through this level of complexity. It is a recipe for catastrophic failure and massive technical debt.
Which is why we need a standardized blueprint for the entire industry. And that transitions us perfectly to our final source, the Draw PSS paper on standardizing knowledge engineering practices using reference architectures, or RAs.
A reference architecture is a concept heavily borrowed from traditional physical engineering and older software paradigms. The paper cites AUTOSAR as the prime historical example, which stands for Automotive Open System Architecture.
I was really fascinated by this comparison. How did AutoSAR work in practice?
Well, before AUTOSAR, every car manufacturer built their software components differently. If Ford wanted to integrate a braking system from Bosch and a cruise control system from another vendor, it was an integration nightmare.
Because none of the systems talk to each other.
Exactly. The software didn't speak the same language. AUTOSAR provided a standardized blueprint. It abstracted the hardware so that application software could be swapped in and out regardless of the underlying microcontroller.
Oh, that's brilliant.
Yeah. The authors of the drop-based paper are arguing that knowledge engineering and AI agent architecture desperately need their own AUTOSAR.
And they provide a highly structured 6-step roadmap for how a company can actually create and implement one of these architectures. Step 1 is scope and requirements. You have to figure out what your AI system actually needs to achieve before you write a single line of code.
And this is where the paper makes a vital distinction between functional requirements and quality attributes.
Walk us through that distinction.
Functional requirements are what the system must physically do. For example, the system must import common data formats like CSV or JSON, or it must support semantic web standards like the RDF triples we discussed earlier.
While quality attributes are how well the system must do it, right?
Yes.
Like, is the system scalable? Is it domain independent, meaning can I move it from healthcare to finance easily? Is the knowledge curatable by humans?
Exactly. Step 2 is information sources, which just means looking at existing systems so you aren't reinventing the wheel. Step 3 is architectural analysis. Step 4 is synthesis, putting it all together. Step 5 is evaluation, where they highly recommend using ATAM.
The architecture trade-off analysis method.
Right, to systematically spot risks and compromises in your design. And step 6, instantiation, actually building the final system.
But the really fascinating part to me, like the actual mechanical meat of this paper, is where they get the building blocks during step 4 synthesis. They don't just guess. They use something called a boxology.
I love that word, the Swemmel's boxology.
Yeah, SWML stands for Semantic Web and Machine Learning Systems. Researchers essentially looked at hundreds of neurosymbolic AI systems.
Systems that attempt to combine the fuzzy logic of neural networks with the rigid, rules-based symbolic logic of traditional databases.
Right, and they abstracted them into a visual taxonomy. They found 44 recurring patterns. These 44 patterns are the Lego bricks of the reference architecture.
It's so structured.
It is. I want to trace one of these patterns step by step to see how it works in reality. The source gives a very specific practical example of one of these bricks, the F2 pattern. It stands for Fusion 2.
It's an incredibly common pattern for enterprise data. Walk us through the flow.
Okay, so the F2 pattern takes 2 distinct inputs. First, it takes symbolic data like an existing rigid enterprise knowledge graph.
Structured data.
Structured data, exactly. Second, it takes unstructured data like raw scraped text from a competitor's website or a bunch of disorganized PDFs. It feeds both the structured graph and the unstructured text simultaneously into a model like an SVM, a support vector machine, or a modern BERT-based LLM.
And then what happens?
The model processes them, and the output is newly updated, enriched symbolic data that gets fed right back into the original graph.
So it's a continuous learning loop. The unstructured text is used to enrich and expand the rigid graph, and the rigid graph is used to ground the model so it actually understands the text.
The hypothetical scenario they use is a company trying to improve content discoverability on their corporate website. The stakeholders, the business people who don't necessarily know how to code list their quality attributes.
Right.
The system must be scalable, it must understand our highly specific medical domain, and it must be extensible for the future.
So instead of the software engineers guessing how to build that from scratch, the architects go to the SWM boxology. They look at the 44 patterns, and they realize the F2 pattern perfectly satisfies those specific quality attributes.
That is the absolute magic of the reference architecture. It completely bridges the communication gap between the business stakeholders and the back-end engineers. It provides a common lexicon.
It gets everyone on the same page.
The business people say, we need it to be scalable and domain-specific. The engineers pull the reference architecture, identify the F2 pattern as the solution, slot in FalcorDB for the graph database because they know it provides sub-millisecond scalability.
Apply MOMO modularity so the model understands the specific domain without hallucinating.
And wire up the graph loop using TrueFoundry virtual accounts to make sure the model is secure and extensible.
It maps abstract architectural patterns directly to exact business needs. It ensures that everyone, from the CEO to the domain expert to the junior developer, it's finally speaking the exact same language, just like AutoSAR did for the automotive industry.
So why should you, the listener, care about reference architectures or boxologies? Because if you are tasked with building AI in 2026, you do not have to start from scratch. You don't have to wander into the architectural muddy waters blindly and hope your agents don't hallucinate or bankrupt you.
You pull an RA, identify your pattern, slot in your best-in-class components, and you are building on the shoulders of giants.
It accelerates development, it ensures security and compliance by default, and it provides a clear, tested roadmap for scaling from a laptop prototype to an enterprise-grade system.
Let's take a breath and synthesize everything we've uncovered, because we have covered a massive amount of ground today.
We really have. We started deep in the engine room, realizing that traditional graph databases like Neptune and Neo4j, while historically powerful, were bottlenecking AI with network latency and severe 90-millisecond JVM cold starts.
Right.
We saw how FalcoreDB bypassed that entire paradigm by abandoning pointers and using sparse adjacency matrices, turning graph traversals into raw, highly parallel linear algebra to achieve 1.1 millisecond speeds.
Then we move to the map makers, exploring the incredibly labor-intensive world of knowledge graph and ontology engineering.
KGOE.
We saw how massive ontologies completely overwhelm the attention mechanisms of LLMs, and how modular ontology modeling, giving the AI human-centric conceptual modules, acts as psychological guardrails, narrowing the probability space and boosting complex task success from essentially 0 to 95%.
From there, we climbed the 5 layers of AI engineering, leaving the frantic single-agent loop behind to embrace graph engineering. We learned how to build AI org charts with specialized nodes, conditional edges, and shared state, ensuring we isolate responsibilities and only deploy this complex machinery when a fan-out or fan-in task genuinely requires it.
And because fully autonomous multi-agent systems introduce massive enterprise risk, we explored how platforms like TrueFoundry govern the graph. We discussed assigning virtual accounts for node identity, enforcing budget caps to prevent infinite fan-out loops, and implementing structural checkpoints to keep human approval at the edges of the graph for sensitive actions.
Finally, we tied it all together with reference architectures, using the Swemliz boxology and the F2 fusion pattern to show how you can standardize all of these disparate moving parts into a single, cohesive blueprint that satisfies both the business requirements and the engineering constraints.
It's a comprehensive, incredibly powerful stack. But as we wrap up this deep dive, I want to leave you with a final, slightly provocative thought to mull over.
Ooh, okay.
We have spent this entire session talking about how to structure and govern artificial intelligence. Look closely at what we are actually doing. We are building modular ontologies based strictly on human concepts. We are designing graph engineering systems that literally mimic human corporate org charts, complete with specialized researchers, writers, and skeptical reviewers.
That's true.
We are implementing governance gateways that function exactly like middle management approval chains.
We are forcing the AI to work exactly the way a 20th century corporation works.
We are explicitly designing these systems to mirror human bureaucracy. But as these agents become increasingly autonomous, as they run on sub-millisecond math engines like FalcoreDB, and as they begin communicating globally via instantaneous machine-to-machine protocols, it raises a profound question. Are we simply locking these new alien intelligences into our legacy human inefficiencies? Or, as we step back and let these systems run, are we on the verge of these graphs organically discovering entirely new non-human ways to organize, intelligence ways to structure thought, action, and cooperation that we haven't even begun to conceptualize yet?
Wow, that is a brilliant thought to end on. Are we building the ultimate employee, or are we just constraining an alien intelligence with middle management? Thank you so much for joining us on this deep dive into the architecture of intelligence. We highly encourage you to explore the concepts of reference architectures and graph engineering in your own projects. Until next time, keep questioning the blueprint and don't let the architectural waters get too muddy.